Here are the two major ideas that we're going to be looking at for the rest of the video. So if we have T as a linear transformation between two vector spaces V and W, then we define these two sets. The first set is called the kernel of our linear transformation. We usually denote the kernel as KERT or ker-T, and it consists of the set of the vectors in V that get mapped to the zero vector of W. And the second set is called the range of T, and it's the set of all of the vectors in W that come from a vector in V. Let's take a look at a quick example of how to find the kernel in a range for a linear transformation. So we're going to take R2 and we're going to consider the projection operator where we lose all of the y information. So this is a projection onto the x-axis. So let's talk about the kernel first. Essentially what we're looking for is we're looking for the set of xy's that when we go through T, we end up with the zero vector of R2. Now we know the rule for our linear transformation. It projects onto the x-axis, so we lose all of the information in the y component. So this implies that x has to be equal to 0, or that any vector of the form where our first component is 0 and we have any number in the second component gets mapped to the 0 vector. So I want to show you visually what this looks like and why this is the case. So remember that this linear transformation T projects our vector onto the x-axis. So what happens if we start with a vector, say, up here that actually lies on the y-axis? So these are vectors that lie on the y-axis. If we project this down onto the x-axis, we end up with just the 0 vector. We get projected right down to the origin. So that's why any vector that lies on the y-axis gets projected to 0, 0. So it's exactly these vectors that make up the kernel of our linear transformation T. Next I want to briefly discuss the range. So in this example, the range is any vector in R2 that is a result of our linear transformation acting on a vector in R2. All of these vectors lie on the x-axis. So this is the result of our linear transformation. So think of it as going backwards. So if we start out here and we want to work backwards, this vector that lies on the x-axis could be a result of, say, this vector through T. So if we start out with this vector x, this is an image of the vector x under our linear transformation. So this vector down here is going to be inside the range. Same thing could happen over here. So for example, this vector here could be a result of, say, this vector through the linear transformation. So if this is an x, then if we evaluate t of x, that's going to project this vector down onto the x-axis. So all of the vectors that are inside the range lie on the x-axis. So I have a couple notes for you to think about for a few minutes. The first one is I would like you to go back and notice that the 0 vector of R2 is inside the range of T. The 0 vector is also inside the kernel of T. So maybe it's possible that the kernel and the range of a linear transformation are subspaces. It does turn out that the kernel and the range are special sets of V and W. They are indeed subspaces. I want you to think about these for a little while. We're going to actually do the proof for these two on an upcoming worksheet. So I have a second note from that last example that we did about that projection operator. Notice that the dimension of R2 is equal to 2. We know that already. But let's think about the dimension of the kernel and the range. We can talk about the dimension of these sets because now we know from Theorem 3 that they are indeed subspaces. So it turns out that the dimension of the kernel is 1. That's because the kernel is the y-axis, and we know that the special vector j is going to span the y-axis. So it only needs one basis vector. The dimension of the range which is all of the x-axis, is also equal to 1. The vector 1, 0 is going to span that entire x-axis. Now I don't know about you, but there's something peculiar about these dimensions. So notice that the dimension of the kernel plus the dimension of the range happens to be equal to the dimension of our vector space. So we might wonder if this is true in general. Before I answer the question of how the dimension of the range and the dimension of the kernel relate to the dimension of our vector spaces, I have to introduce a couple of definitions here first. So if T is a linear transformation between two vector spaces V and W, we have the following two definitions. We say that the dimension of the range of T is called the rank of T. And we denote the rank of T as just rank bracket T. The dimension of the kernel of our linear transformation is called the nullity of T. And again, we just denote that with nullity bracket T. So here it is, the answer to that question that we had thought up earlier. Essentially, it's an extension of the dimension theorem that we saw earlier. This is the dimension theorem for linear transformations. So if T is a linear transformation, and we know that V is an n-dimensional vector space, then it is true that the rank of T plus the nullity of T will be equal to n. To prove the dimension theorem for linear transformations, we're going to divide the proof up into two cases. The first case we're going to look at is that the nullity of our linear transformation is equal to n. So if the nullity of our linear transformation is equal to n, that means that the dimension of the kernel is equal to n, or that the kernel needs n basis vectors. So I'm going to represent that basis as capital B here. So I'm going to say V1 up to Vn, this is the basis for our kernel. Now B is a basis. That means that the vectors V1 all the way up to Vn span, but more importantly, they're linearly independent. So we have n linearly independent vectors. All of these vectors are inside of our vector space V, so they must also be a basis for our vector space V because V has dimension n. Since V1 to Vn form a basis for our vector space V, that means that we have the following. It means that we can take any vector from our vector space and we can write it as a linear combination of those vectors inside the basis V. And what we're going to do is we're going to apply the linear transformation to this equality. Because T is linear, we can break this up by property number 4 that we saw earlier. And we get the following expression. And now this is where the magic happens. We know that V1 all the way up to Vn are inside of the kernel. So T of V1 is equal to 0, T of V2 is equal to 0, all the way up to T of Vn. All of these values are going to be equal to 0. So we get a1 times the 0 vector all the way up to an times the 0 vector. And all of this is just equal to the 0 vector. So this means that if we start with any vector in our vector space V, T acting on that vector sends it to the 0 vector of W. So the only vector inside the range of our linear transformation is the 0 vector. And that means that the dimension of the range of T must be equal to 0, or that the rank of T is equal to 0. So if we look at our dimension theorem equation, we have rank plus nullity will be equal to 0 plus n, which is equal to n. For the second case, we're going to assume that the nullity is somewhere between 0 and n. So of course the nullity of t has to be some kind of integer value here. So I'm going to assume that the nullity of t is m, where m is somewhere between 0 and n. So here m and n are going to be integer values. That means that we need m vectors to form a basis for the kernel of t. So I'm going to let b here be the basis for the kernel. So it contains the vectors v1 up to vm. Now all of that theory we did with the plus-minus theorem allows us to extend b to a basis for our vector space v. And I'm going to write that extended basis as b prime. So it starts with v1 all the way up to vm, and then we just keep adding vectors into b until we get to a basis for our vector space. So next what we're going to do is we're going to set up a set S. S is going to contain the following vectors. We're going to have t of vm plus 1 all the way up to t of vn. And what we're going to do is we're going to try to show that S is a basis for the range of t. We're going to start out the same way that we did last time. We're going to use the fact that v1 all the way up to vn is a basis for our vector space v. So if we take any element v from our vector space, we can express it as a linear combination of those n vectors. And what you want to do is you want to apply t to both sides. I got a little lazy here, so all of this expression here would be inside of the brackets. And because t is a linear transformation, we can factor out all of these ai's and have t of v1 up to t of vm, t of vm plus 1, all the way up to t of vn. Remember that these vectors v1 all the way up to vm, they're inside the kernel of t. So when we go to evaluate t of v1, we know that's equal to the 0 vector. And we do this for all of the vectors all the way up to vn. We know t of vm is equal to the 0 vector of w. So that leaves us with only these vectors remaining. So what we've shown is we've shown that t of any vector from our vector space v is equal to a linear combination of these vectors, t vm plus 1 up to t of vn. So what we've actually shown is that these vectors here span the range of t, because this is an element of the range of t. This is where things start to get a little crazy. What we're going to do is try to show that this set S is linearly independent. So we're going to set up the linear independence equation. So that's what you see right here. So I've used all of these k's as the coefficients of our vectors here. And I set it equal to the 0 vector of w. We know that t is linear, so we can actually combine everything on the left-hand side of this equation to get this expression right here. So what does that tell us? It tells us that this particular vector here gets mapped to the 0 vector of w. That means that this vector here actually is inside of the kernel of t. Well, if this vector is inside the kernel of t, we can rewrite this vector as a linear combination of those basis vectors that we started with in B. So what I've done here is I've expressed this vector as a linear combination of the basis vectors of the kernel. And what we're going to do is we're going to move all of these vectors over to the right-hand side so that we get the 0 vector on the left-hand side. So all I've done here is I've just subtracted this one and subtracted all of them all the way up to kn vn. So now we have a linear combination of the vectors v1 all the way up to vn. We can use the fact that b prime, which contains all of these vectors, is a basis. So all of these vectors are linearly independent. All of these coefficients must be equal to 0. In particular, we're interested in these ones. We're interested in km plus 1 all the way up to kn. And all of those are going to be equal to 0. So we've shown that the set S is linearly independent as well. We know that S is a basis. You can go back and check that it is actually a basis of n minus m vectors. So that tells us that the rank of our linear transformation is going to be n minus m. So when we add together the rank and the nullity, we do indeed end up with a value of n.